afternoon. Good afternoon. My name is Dale Brocious. I'm the Chief Commercialization Officer for IACME, the Composites Institute based in the U.S. We've got a great program for you this afternoon. Thank all of you for coming this afternoon. I've done this 3 years in a row, about sustainable transportation. And every year the topics are different. So whether it rolls, flies, or floats, we all worry about lowering the amount of energy that's required to propel something forward. So today we have, I know you didn't come here to see me, or maybe 2 of you did, but the rest of you are here to see the speakers. So without further ado, I want to introduce them. Our 3 speakers are Andrea Fagiani, the head of Composite Materials and Technology Center for Automobili Lamborghini. Baptiste Wossi, VP of Engineering of Aero, and Philippe Pepin, R&D Composites Engineer from Air Liquide. Gentlemen, please come on stage. Okay. Just make sure this is on. Not getting any sound. There we go. Okay. So just so everybody knows, after the 3 speakers are going to speak, and then we will take questions after that. I'll ask some. We'll have opportunity for a little bit from the audience. But at the end of the presentation, at the end of the hour, all of the speakers, we will be out in the speaker area, welcome area, so you can come and engage, ask your questions personally, exchange business cards, and go from there. So our first speaker is Andrea Fagiani. He's the head of Composite Materials and Technology Center at Automobili Lamborghini. So Andrea, the stage is yours.
Thank you very much, Dale. Good afternoon, everyone. So without further ado, I'll make a start. So thank you to JC for inviting me today. So my talk is going to be about innovation on the Lamborghini Revuelto, which is the latest Super Sportiva by Lamborghini, and the sustainability challenge that lies ahead of us and how we were tackling that at Lamborghini. So my presentation is going to be split into four sections. The company, just a very brief introduction. What we do in my team together with my colleagues in terms of innovation and core competence in carbon fiber. Then I'll go into a bit more detail about the Revuelto, mainly the chassis and the front frame. And then the last section will focus on sustainability and how that relates to carbon fiber for us at Lamborghini. So the company. The company was started in 1963 with Ferruccio Lamborghini founded the company. And I'm not going to go through all the details, but since then, it's been a gradual and quite impressive expansion. So I'll point out a few notable dates. In 1998, we joined the Audi Group. In 2003, there was a plant expansion up to 30,000 square meters. And then gradually, it's been a growth in surface area to the size that we are today. And in 2023, we launched the Revuelto, which is the main focus of the talk today. So you can see some of the iconic cars. And if, like me, you grew up dreaming of these cars, you know these are iconic vehicles, not just for car enthusiasts, but for anyone really. So we've got the Miura, which redefined the sports car concept, the Spada, the Countach, with its, with the iconic scissor doors, and the LM002, the first super SUV in history. So in summary, what does Lamborghini strive to do? They want to present iconic models, pioneering their own new segments. And what are the cars that Lamborghini does today? So the pyramid there shows basically the different cars by volume. So the 3 model lines, which are the Revuelto, the Huracan, and the Urus. Then above that, we have derivatives of each one. So we go to lower volumes, and then we move up the pyramid like this. We have a few off cars where we make let's say roughly 100. And then we have the one-off, which are really special one-off cars with innovative technology and where we want to demonstrate the technology for future cars that are coming ahead. So these are all road legal models. And then underneath there, you can see we've also got track-specific models. So moving on to innovation and what do we do more specifically in my team together with my colleagues. So what's innovation? Innovation is developing new products, designs, and ideas. They need to have a distinctive design. The cars need to be fun to drive, have a high performance. They need to be lightweight to achieve that. And they must show the cutting edge technology. And all these things have to come together. So it's a lot of research, speaking with our suppliers, manufacturers, universities, institutions, exhibitions, such as this one, and our customers. And all that put together gives you innovation. What do we need to do to achieve our ambitious innovation targets? We need to work as a team. Everything starts with an idea. It then moves with development, be that aerodynamic, materials, on track. And where does carbon fiber comes in? Carbon fiber comes into making all of it real. And what do we do specifically in my team? So we have worldwide scouting. So we need to be aware of all the trends, all the new materials, and how we might apply them. We need to understand them. How can we customize them to suit what we specifically need to do? And how do we incorporate those materials in the technologies that we want to use on the different cars? So the first, how do we develop a new car? We start with what are the requirements? So what volume? I showed before the pyramid. You have different technologies which are suited to lower volumes, like pre-preg technology, or if you need higher volumes where you need to produce more cars per day, then you need to go to a different technology. What's the life cycle of the car? And obviously, what are the costs? We then move on to a building block approach, where we start with testing materials, coupons, or something very small, and we slowly build up the complexity. Obviously, the costs rise as you go up the pyramid, so you want to be doing less and less tests. So each block gives you the confidence to move up the pyramid. So the next phase is testing. You have to follow a concurrent engineering approach together with all our colleagues in all the different areas at Lamborghini. We have to do design for manufacturing, where it can't just look good on paper or in a numerical analysis. How do we make it real? So we have to design for manufacture. So it's a constant process of materials, the process we use those materials and the final product. And then we have to make a business case. So we want to use this technology, but how does it stand in terms of costs? And how can we make a positive business case to make it happen? And then the last step is validation. This starts all the way from the bottom of the ladder. So we have to test our materials. We have a test lab where we can do all of this, or most of the things that we want to do. We generate our own material allowables. They can't just be taken from a data sheet. They have to represent how we're going to use the material. So that might have the material might be influenced by the manufacturing process where it's going to be used. And then the test phase is materials. Then we go up the ladder again, elements, sub-assemblies, components, and then finally something like a full vehicle crash test where everything has to come together. We follow the standard VW Group validation. So not just all the structural requirements. We have very stringent Class A aesthetic requirements, and this applies to everything. The chassis, which is the focus of the presentation, but also body panels and all interior components. So I'll try and explain a few of the main features of the Revuelto monocoque. So in 2023, Lamborghini unveiled the Revuelto with what we think is a revolutionary monocoque. So why is it so? Because it's a multi-technology carbon fiber concept where each section of the chassis is picked to be the technology it is for a specific reason. So we're using forged composites, where we won a JEC award, which I'll talk about a bit later. I think it's on the next slide. And this is a significant step forward from its predecessor, the Aventador, in terms of torsional stiffness, weight, and driving dynamics. And it's the first super sports car to be fitted with 100% carbon fiber front structure. So the image on the bottom right is basically what you have to do. What are all the things that have to come together to make this reality? It's new concepts, new simulation models, new test methods, new materials, putting this all together into new technologies to develop the new architectures which form the basis of what you can see there. So in terms of technology, I touched upon it before. So the motto has to be using the right materials and the right technology at the right place. The image in the middle shows you how we're using different technologies and bringing these together to build the whole chassis. In red, you can see sort of traditional autoclave prepreg technology for the roof area. In green is the CSMC, so short fiber pressed technology. And then we have the structure called the rocker ring in blue, which is an RTM technology where all the primary load paths are managed through the structure. So how do we pick? The difficulty is picking the technology for the right thing. So there's many requirements: geometry, aesthetics, fixing points, so basically design constraints, static and dynamic loads, so the aero loads, the crash tests, everything has to come together, crash performance, and yeah, of course, aerodynamics. And in terms of the cell structure, we have these constraints, but then what drives our decision-making process is how long do we have to develop this? What are the requirements in terms of homologation? What are we targeting in terms of weight? And what is the cost? You know, there's always a trade-off. Often it's down to weight against cost. So, you know, do we have a weight target that we want to push and we want to spend more to achieve that weight target? Or do we, you know, it's again, it goes back to the business case that I was mentioning before. And then production rate. You obviously can't make a full car in prepreg autoclave technology if you need to make 30 a day. So picking the right technology, taking all these things into account is absolutely critical. And as I said, yeah, the design is optimized thanks to large use of forged composite technology, for which we won an award here at the JC in 2016. I won't go into too much detail here, but the main advantage is that it's relatively cheap compared to the other technologies, and you have a lot of freedom in the geometries that you can make as it's in the press. And it optimizes efficiency, reducing production time. So again, it's about picking, this technology isn't suited for everything. Where do we pick it and why? And how do we combine it with other technologies to make the chassis the full component that it needs to be? This is the what I mentioned before, the rocker ring on the bottom left. So the main load paths, which aren't suited to short fiber technology, we manage those through higher material characteristics, long fiber. So this is made in RTM. And yeah, for the Revuelto, we developed this as basically a ring that's outside the tub and manages all the crash loads mainly that come from the front and have to travel through the car and out the back. And then also the A pillar and the A2 pillar, which you can see on the right, they've been merged into single components, so saving weight because you're making less components. So you're saving complexity and weight by doing that. And then obviously the roof I mentioned before in the diagram is a more traditional prepreg technology. It's no less efficient. So it's prepreg material, and it's retained. We retain that in the roof area. And this is for the high technical, aesthetic, and quality requirements that needs to have. And then it all comes together, you can see there. And then this is just a slide showing the front frame structure. So the front frame has to manage the crash loads during a crash test. So we used CSMC technology in green for the cones because these are very high specific energy absorption compared to aluminum. So again, you can make a lighter structure because it absorbs more energy with the same amount of material. And then we retain mechanical joints between the parts so you can replace and decouple the front structure from the monocoque behind it in case of an accident. So yeah, so this is just a slide showing how everything comes together. The monocoque together with the rear structure, which is still which is metallic. So it's a rear frame in high strength aluminum, rear shock towers and hollow casting, and then everything comes together with a composite front end to give us 25% torsional stiffness compared to the previous generation, and 10% lighter weight. So we're obviously chasing stiffness, performance, weight, and using the right technology in the right area to achieve that. And now this brings me to my final section. So what's the sustainability challenge? How does all of this, how do we make it sustainable, and what are the challenges that lie ahead? So what's sustainability for us? For us, sustainability is what responsibility do we have? Does each one of us have? So we need to develop what we call a concept of sustainable development. Everyone needs to behave responsibly to conserve natural resources. And then how do we protect global ecosystems now and in the future? So that involves training and education, and then also the correct action and communication. So, you know, sustainability is also the workforce. So, you know, how do we support the health and well-being of individuals so they can, you know, give the best that they can. So that has to, be through action and communication. So this is just a picture of ESG framework. So we have a holistic vision on sustainability, which is environment, social, and governance. The environment obviously is a decarbonization program using sustainable materials and trying to build a circular economy around those materials. Socially, this is a corporate social responsibility, diversion and inclusion, sustainability rating for all our suppliers, so making sure that all our suppliers are sustainable, not just what we do in-house. We were voted in Italy top employer for many years in a row. And then also the culture in each and every one of us when we go to work has to be one of sustainability, both towards our colleagues and towards the company as a whole. So sustainability is constantly in our KPIs and in the management objectives that the company sets. We have a very clear compliance and integrity policy, anti-corruption and risk management. So all these ESG frameworks are very clear for each one of us to follow in our day-to-day work. And then in terms of carbon fiber, how can we make everything more sustainable? So on the left, what we're trying to show here is, for example, if you have an autoclave technology using water, nitrogen, and electricity, can we move, always questioning our choices, can we move more to a press technology where we reduce, for example, the electricity usage or how much energy we're using to develop the same end product? And this has to tie in with a pyramid in the middle. So how does that fit with how many cars you're trying to make for each kind of model? And then also on the right, what I'm trying to show is both for thermosets and thermoplastic composites, how can we try and recycle and reuse our fiber? And then we have the whole topic here of bioresins and finding applications for our waste products, which you can see here. So, roughly speaking, a quarter of the carbon fiber on the car is scrap. So we need to find ways of using that scrap material again. We see two ways of doing this. One is probably the, let's say, shorter term solution, using it in functional applications where aesthetics is not involved. So we want to use them to reduce weight and improve performances, where we substitute components with their equivalent recycled counterparts. And then the second step will be, how can we also pass the stringent aesthetical requirements that we have by making Lambo material? So can we make a new material which is made from this recycled that can be a selling point and become a new part of the DNA for Lamborghini moving into the future? And yeah, thank you very much. And yeah, thanks to the JEC for allowing me to present here. Yeah, and I'll pass you over to my colleagues.
Thank you very much, Andrea. Just a reminder that we'll be doing the questions at the end of all three presentations. So we'll move straight on to our next presentation. I'm pleased to welcome Baptiste Rossi, the Vice President of Engineering from Aero.
Hello. So on my side, I'm going to talk to you about sailing boats. And at Aero, what we are trying to do is to reintroduce sails on a commercial ship, like the one you can see here. So today I'm going to try to explain to you a bit how these sails are working, how they are made, and how we are organized at Aero. Just to start, the background, we are evolving in the maritime industry, where we know that 90% of the trade over the world are made by ship. And the number of trades is going to double from between now and 2050. And in parallel of this, the ships are using still a traditional engine, which are with high level of carbon emissions. And these conclusions are made by a lot of people, and particularly by the IMO, who is ruling the world of shipping. And IMO is starting to introduce taxes to try to reduce the carbon emissions of the ships, and that's where our product is interesting for ship owners. The idea of the technology we are developing at Aero is coming back from 2010, when a trimaran was raced in the America's Cup, and this trimaran was equipped with a rigid sail, This sail was more efficient than a traditional sail. We estimate that such a rigid wing is 2 times more powerful than a traditional wing with the same size. So it was more powerful, more efficient, but there was also another thing which came out, which was that this kind of sail was easier to control and to introduce on boat with a fully automated control, and they would not require a specific crew to be operated. And from this idea, we tried to develop sails we could fit to commercial boats. In 2016, we've done a first prototype, which showed that we could make a sail fully automated. In 2018, we developed a small version of our wing, and this sail, 2 of these wings were fitted to a boat called Energy Observer, which is a demonstrator of all the ways you could have to power a ship with green energy. So you can see the solar panels, wings, and there's the hydrogen as well. This ship has been running all over the world with the sail, and we could see that the sail were quite efficient on this boat. And they were the only technology which was not requiring any batteries. So the wind, you always have it, and that's they could see that every day. And then in 2023, we produced our 4 first wings to equip this boat, which is called Canopy. And this boat is going from Europe to Kourou in Guyana, to transport some part of the Ariane 6 rockets. We'll come back later on Canopy. At Aero, we are doing all the engineering to first define the performance or evaluate the performance our wings could bring to the table for a new ship. And we are designing the products. The products are wings, so we are designing the structure of the wing, but we are also designing all the actuators, the control system, and the software to run this control system. And then we are doing services as well to install the wings on the ship, to maintain them, and also to collect the data and analyze them. Canopy is a 121 meter ship. So the wing on Canopy were installed in August 2023. It's running at 16 knots. And we've been doing, they've done 2 cross-Atlantic now. And we can measure the gain from our wings. And we estimate that the gain in fuel consumption is about 35% on Atlantic crossing. So we are still talking about an hybrid system between the between the traditional engine, and the wings. And the way it's working is we've got a target speed, and we try to maximize the use of the wings to reach this target and to minimize the use of the traditional engine. The way it works, it's pretty simple. You've got wind sensors on the ship, which are giving you the speed of the wing and its direction. And then we've got a software which automatically is taking into account this data, is going to set up the wing with the right angle, the right camber, to produce the most efficient power. The main characteristics of the wings, first, we've got a wing which is made of 2 elements, like a wing on a plane, but working vertically. As I said, the performance is about 2 times better than a traditional wing with the same surface area. The wing is totally automated. This means that the wing can rotate at 360 degrees to be aligned with the wind direction. It can also, you've got 2 elements. The secondary element can rotate as well to adjust the camber. And by adjusting the camber, we are adjusting the power delivered by the wing. And in the case of canopy, the profiles are made of fabric which is tension between ribs. And this profile can be raised or lowered, which means that we've got the main structure always standing up. But if the weather is too hard or if you're on port, you can lower the sail. This is also totally automated. And in terms of operating window, we've got a system which can produce power from a wind coming from 5 degrees on the front and then going all the way to a back wind. In terms of composites, the full structure of this wing is made of composite. So when I say full structure, it's what you see on the screen here. We've got 2 masts. The main mast is 37 meters high. We've got a secondary mast, and then both masts are linked by a boom on the bottom part and a crane on the top part. And then along this mast are some ribs. And between these ribs, we are tensioning some fabric. And these ribs are in composite as well. We had to dimension this structure to sustain up to 100 knots of winds and also to sustain hard sea conditions. So you can imagine that we had to have a very robust structure. But at the same time, given that we need to not to be obstructive on the ship and keep the ship performances and balance. So we had to have a light component as well, which is where the composite is becoming particularly interesting. Sorry. It is also interesting compared to steelwork, for example, because in terms of fatigue, the composite is much better. And on the kind of ship we are working with, the lifetime of a ship is 25 years, and you don't have many opportunities to maintain it because the ships are going over the world all the time with a good check every 5 years. But between that, we really don't have a lot of access to this ship. So here we go, and this wing, so I said it's 37 meters high, and it's less than 40 tons because we are using composite materials. Our colleagues doing same kind of technologies came up with products which are much heavier than that because they are not using as much composite as we do. And yeah, now basically we keep going, trying to continue and develop these products, and that's why we are here today. There's a few of my team and colleagues here, trying to find even better solution to keep the level of robustness high and trying to lower the cost as much as possible to be able to have more and more ship equipped with such a system and try to decarbonize the maritime industry. That's it for me. Thank you.
Thank you. Thank you, Baptiste. And again, we'll get to the questions for Baptiste as well at the end of our next presentation. So our next presenter is Philippe Pepin from Air Liquide. And he's going to be talking about the fuel of the future, which is hydrogen. And our Air Liquide is setting us up for a success there.
Thank you very much. Good afternoon, everyone. And my presentation today will be about advancing Type 5 technology for efficient and sustainable distribution. Then I will present the results that we have so far in a European project called Road Trip. That project has been financed by the Clean Hydrogen Joint Undertaking. And the objective of that project is to develop a trailer made out of Type 5 thermoplastic composite cylinder in order to transport as much as possible hydrogen. Then the content on my presentation, I will explain the origin of that project, why are we in that project, the approach, what we achieved so far, and the conclusion. And first, I'm going to present the consortium. Then there is of course Air Liquide. We have an expertise in hydrogen. There is a Belgian company called Coves. They developed the Type 5 thermoplastic composite cylinder. There is Arkema. It's a French chemist that supplies and develops the raw material. The University of Wrocław in Poland. Then they will be doing an extensive cylinder testing. Effectis. It's a French company, experts in large-scale fire testing. Segula, they are doing the design of the trailer and the life cycle analysis. And Vitest, they are in Poland, and they will be working on decontamination. And the University of Piprim in France, that will be studying the compartment of the material and the cylinders in fire. Then first, why are we in that project? Then if you look on the sketch that is on the left, you can see that there is a growing demand of transportation of hydrogen, and especially gaseous hydrogen. Therefore, we need to improve our supply chain by transporting more and more hydrogen. Then so far we can use Type 1 trailers made out of steel. They can transport at the maximum 300 kilograms of hydrogen. Then now we have composite trailers. They can carry 900 kilograms of hydrogen, but the main target we have is to be able to carry 1.5 tons of hydrogen. Then the objective we have in that project is to design these cylinders called Type 5 and to be able to dry these cylinders to be able to develop, to deliver the hydrogen at the requested purity, to demonstrate that these cylinders are safe to use, and also that we can make this cylinder with high pressure, with a maximum cost of 400 euros per kilogram of hydrogen stored, and that the final product has a good environmental footprint. But we must not forget the regulation aspect, which has to be taken into account. Then now, our approach. I presume that you have already heard that to transfer more hydrogen, you can go to 700 bars, but that is not necessarily the best working pressure of the cylinder. Then our approach is very different. We took into account the maximum allowed mass of the trailer on the road. We design the trailer, all the metallic parts, and the remaining mass is for the cylinders. And if you know the number of locations of your cylinder on the trailer, you know the mass that you have for every cylinder, and therefore you know the working pressure. Then one of the output of this project is to know the working pressure that we have of the cylinder we have to put in our trailer in order to transport as much as possible gaseous hydrogen. But the final product has also to comply with usages. Then we need, and it's not obvious to understand, that we have to dry the cylinder. Then when a composite cylinder or metallic cylinder is made, it is pressure tested at 1.5 times its working pressure with water. And afterwards, you have to remove water and you have to dry the cylinder. Then the reason why you have to dry the cylinder is because people don't want to wait at the hydrogen station or the petrol station. Then when the gas arrives at the hydrogen station, it is compressed and propelled in the cylinder of the car. if it is not cooled down, the cylinder of the car will go at a higher pressure than the one allowed. And therefore, we have to cool down the hydrogen. And to do so, the hydrogen goes into a pipe that is in a liquid nitrogen bath. And therefore, if there is too much water in the hydrogen, it will freeze in the pipe and you will never be able to fill the tank of your car. Then the hydrogen has to have a water content less than 5 ppm, which is quite low. And to do so, we do cycles of compression and vacuum. Compression, vacuum, compression, vacuum. And after a while, after several cycles, we can reach that target of 5 ppm. And that cannot be done with type 4 cylinder, the standard cylinder that we can buy on the market. And that is a drawback. Also, the cylinder must be collapse-free. Then the liner in the cylinder must not collapse when you defuel the cylinder from high pressure to low pressure, for instance, from 500 bars to 200. If you do it too quickly, the liner can collapse. And also, of course, it has to be compatible with hydrogen. Then to reach the goal, we developed the Type 5 cylinder. Then Type 5, it's only a name. Actually, it doesn't exist. According to the norm, it is a Type 4. But as it is very different from Type 4, the company that developed that cylinder called it Type 5. But it's a Type 4. Then this cylinder are made with the material developed by Arkema called UDX PA11 type. They are continuous fibers impregnated with polyamide 11 resin. And basically, it's a resin that is 100% bio-based with quite good mechanical properties. And it is processed by Coves, and they managed to make a cylinder with a monolithic structure. And I call monolithic structure. If you look on the sketch on the right, you can see that in standard type 4 cylinder, you have a polyethylene liner with a composite epoxy structure, and that is not monolithic. There are two different materials. With the technology of Coves, they managed to have one layer made out of the same chemical, but on the first 2 or 3 millimeters of the inner part, which is the liner, you do not have any fiber. On the remaining thickness, you have roughly 60% of fibers in volume, but it makes one layer. And therefore, you can understand that it's much easier to do vacuum on the cylinder and to use the standard equipment that we use in filling centers to dry a cylinder. And also, you can see it on the sketch. You can save some weight, some volume on the liner of the Type 5 cylinders because it's very thin. And we took the opportunity to change a little bit the design of the shape of the dome to be able not to have too much water remaining in the dome. Then some word on the regulation aspect. I'm not going to be too long on that, but you have regulation well known for hydrogen cylinders and equipment, for transportation, and for the hydrogen station. The challenge is to be able to have regulation that will allow you to use your trailer at the hydrogen refueling station. And one of the output of that project is to make recommendation to the regulator to be able to do that. Now, on the safety aspect, we study the failure scenarios, and we found three of them. It's a rupture of a hose, a leakage on feeding hose, or piping. And if you have a leakage, and in the case you have a fire, without mitigation measures, you can have what they call a jet fire that can be up to 70 meters long. And our next job will be to find the best protection to avoid that. Now, about the life cycle analysis. Then we took the example of 1 kilogram transported over 100 kilometers on a trailer. We compared so far we compared type 1 and type 4 cylinder. And we can see that on many aspects of the many environmental aspects, which can be CO2 emission, fuel emission of mineral resources, we still have quite a good saving for type 4 compared to type 1, and that can be quite easily understood as with the type 4 cylinder, you have to make less trip to deliver the same amount of hydrogen compared to type 1. Then now, the conclusion. Then so far we have been working on the trailer design, and we'll continue to do that. We develop also the thermoplastic type 5 cylinder that as an objective is to comply with the norms, but with also with our usages, and we work on the regulation aspect, and we've made the design to safety approach. Then now on the following years, we still have 2.5 years on that project, is we will carry out an extensive testing of the type 5 cylinders. We'll finalize the trailer design, and that will give us a good idea of the optimum working pressure to store 1.5 tons of hydrogen in the trailer, and we will study the compartment in fire of the tank, and the objective also is to simulate that compartment based on the thermomechanical analysis of the processed material. We will look also we'll carry out tests, but relative to usages, which is drying test. We need to be able to dry these type 5 cylinders with existing equipment in filling centers, as we do for type 1. And we will carry out also filling and unfilling testing in order to find out the optimum parameters, just to make sure we never go below the minimum allowed temperature and never go above the maximum allowed temperature. And finally, we will finalize the life cycle analysis for the type 5 cylinders, which we hope will be better than the type 1, as the resin we use is biosourced. Thank you.
Thank you, Philippe. So all of our speakers have moved very quickly through these 3 speeches, and so it gives us a little time for questions. So if you have a question in the audience, hopefully we have a hand mic somewhere out there that somebody can bring to you. So, if you would stand up, let somebody know. But in the meantime, I'll kick things off. And I will start with Andrea. What composite innovations used in the Revelto can find their way into the other high volume platforms at Lamborghini?
So as I touched upon on the presentation, obviously the Revelto is our top of the range car with the lowest volumes. So that blends itself to having, the top of the range technologies. If we go the other opposite end of the scale on the Urus, where we have to make many more per day, you can't A, afford because of the cost, and B, also actually make that many components as you need to do. But some of the technologies still apply there. So we have carbon packages for the exteriors, for the interiors, looking into using recycled materials, for example. So higher volume vehicles would blend themselves more to some of the technologies which are lower cost and allow you to make more parts per day. So less towards pre-preg, but more towards something in the press, which has higher investment costs, but then your part price is lower. So you're going to make more of them. You get your money back, let's say, but then also you're capable of making the amount that you need per day.
Thank you. And if we have a question out here yet? Not, Baptiste, how does Canapé's hybrid propulsion system compare to other sustainable alternatives in the shipping industry?
You mean other wind propulsion system?
Yeah, for wind versus, say, sustainable fuels or other things.
Okay.
CO2 footprint or other measure.
let's say it's different. And if we want to target carbon emission reduction, I think we will have to couple anyway few of these technologies together, to be honest. All the alternative fuels are still fuel with price which are going up and down, which have to be produced. In our case, I mean, we are only using wind, so it feels much better. But at the other end, if we want to reach the targets to really decarbonize fully the industry, we will have anyway to couple a few solutions. So I'm not sure if that's answering your question. I think we won't be the only one, and we will have to work with the others to make it happen.
So today, there's only the one ship that is equipped with the sails. What's in the pipeline? What's next? And what challenges do you have to overcome to have other shipping companies picked up the technology?
We are talking with other ship owners who have different kind of ships. Canopy is a small ship for the industry of shipping. We are talking with ship owners for cargo, for example, where there's not a lot of room on the ship to put wings, but it's possible. And now we have to work together with these ship owners to make new ships which are done from scratch to have these wings on.
Okay, thank you. Philippe, how can this Type 5 hydrogen infrastructure transportation be integrated into the existing infrastructure of fueling systems? You know, I mean, are we going to see these tube trailers at a typical petrol station, or how will that be integrated?
Basically, these trailers are designed to transport hydrogen from the factory that makes the hydrogen to the hydrogen refilling station, and that's and usually if you go to a hydrogen refilling station, you can see behind your wall the trailer, and the trailer has around 100 of these cylinders, or a little bit less or a little bit more, at high pressure, and it's delivered to the station, compressed at higher pressure if needed, and injected in the tank of the car up to 700 bars. Now, if you take the Mirai car, for instance, it's a typical car. The working pressure will be 700 bars. If you take buses, usually they fill the tank of their car at 350 bars.
Was there a question out in the audience that somebody has come up?
Hi,
Yes.
my name's Stella Job from Graysbrook Innovation.
Hi, Stella.
Question for Philippe. Do you have any issues with permeation of hydrogen through the Type 5 tank, or alternatively with effect of the hydrogen on the materials in the way that you get embrittlement with some metals?
We have embrittlement with metals. That's what we have low strength steel. It's what we use. But in the case of a Type 5, as I explained, it's only one layer. Then, for instance, you have no gap between the liner and the composite structure, as you can have with Type 4, which is where hydrogen can go through the liner and escape between the liner and the composite structure through the bus. You have only one layer, meaning that when hydrogen goes through the liner, it will be in contact with the composite structure and will face really the full amount of carbon fiber, which is crystalline structure that will stop as much as possible hydrogen. And the first measure of permeation that we did showed that we have permeation, of course, but it's a very low amount. It's one of the lowest amount that we found.
Okay. We have another question from the audience. So I'll ask Andrea, you know, where is Lamborghini on the curve of electrification for sports cars, and how does the Revelto help you get there?
So in terms of the company, obviously there's a process, a program to electrify the range. But focusing on composite materials, I would say that there's going to be major challenges in the future as cars move towards electrification, not just for Lamborghini, but for any car manufacturer involved in composites. So for me, there's two main things. The first one is range. So obviously range is a big topic. How do we make electric cars go further? So then it's the weight that matters. So composite materials will be key in reducing the weight anywhere we can on the car. And the second one is obviously packaging. These batteries that weren't there before lead to packaging constraints. So we have to have more extreme shapes, geometries. So again, we have to maybe use new technologies or current technologies differently into being able to deal with those packaging constraints in our carbon fiber structures, such as the chassis.
Okay. Baptiste, we were talking in the room before about the technology that you use. Can you explain a little bit more about the manufacturing process of the sails, and and maybe what you can pick up here at the show or at from other industries that you'd like to implement?
Yeah, well, we try to base our design on existing technologies, and one of the main one we've been looking at is the blade industry. And so basically, the masts we are making are made in a similar way as wind blades, in a resin infusion with a double part mold. And we keep looking at what is done in this industry, actually, trying to take all the development which have been done over the years. We used to say that we are where the wing blade industry was 20 years ago, basically, even in terms of regulation and process and development of the process. And basically, we are trying to catch up using what is existing and which is already great for us to work with.
Okay, thank you. Well, it looks like I can see the clock. We're down to less than a minute. Did we have one more question out there? We have to go quick.
Thank you. Hannah Swinburne from the National Composite Centre. One for Lamborghini. Where does the carbon chassis come into the end-of-life vehicle directive? Is that something that is a challenge for carbon full monocoque?
Sorry, I didn't hear the question.
Oh, sorry. Is having a full carbon chassis a challenge with the end-of-life vehicle directive or recyclable materials?
Well, I think, as I mentioned before, I think there's two different, not different, obviously they're highly related, but two topics. One is the performance side, so like the things I showed on the chassis, achieving the performance you want, the weight you want, and then the second stage is how do we get recycled materials to have the performance we need to match the performance that we have now. And then the second stage, which is probably even more of a challenge, is the aesthetical challenge. So how can we make the recycled materials pass the aesthetical requirements that we have nowadays?
Okay, so we've come to the end of the time. Just a reminder that all three speakers will be available over in the speaker meetup area, which is outside the door and to the right. Again, please give a great hand to our three speakers today, Andrea Fagini, Baptiste Volsi, and Philippe Pepin. Thank you again for your contributions.